All right, so here's the setup for number 16. We have a point charge, which is the big guy. Okay, we have this big charge here, 9 times 10 to the negative 9 coulombs, and it's located at the origin. So just imagine here's y-axis, here's x-axis. How much work is required to bring a positive charge of 3 times 10 to the negative 9 coulombs? So that's going to be this guy. I'm going to introduce him in a minute. We're going to take this guy, and where is he starting? At infinity. Okay? So we're going to move this little guy. This little guy is going to come into the problem. He's going to start at the location of infinity, and we're going to move him to the location of x equals 30 centimeters, which is 30 centimeters away from the big guy. So this point right here. So this point from the big guy over to that point is 0.3 meters, and then our other point is infinity. So just imagine like you start going away from this charge, farther, farther, farther. Whoa, man, really far. Oh my gosh, super far. I am so far. It's infinity. Okay, now what's the significance of infinity? Well, look, in this chapter, one of the equations that you learned is how to calculate electric potential at a distance from a big guy, KQ over R. And just note, that's very, very similar to finding electric field at a distance from a big guy. This is the equation for electric field at a distance from a big guy. This is electric potential at a distance from a big guy. Which of these two is a pain in the butt? The electric field. What makes electric fields a pain in the butt? They are vector, right? Electric potential is scalar. Why is electric potential scalar? It's all about energy. Can you put a direction on energy? No. Why is electric field vector? Because it's all about force. Can you put a direction on force? Yeah. So anyway, I just wanted to mention that. All right, now, so back to the idea of infinity. What is the significance of infinity? Well, look at the equation here for electric potential. This is what we're going to be using. If R is infinity, then what happens to V? It's 0. So we got 0 volts there. Now, what we got to do is calculate what is the electric potential at this point right here. So we're just plugging into this equation. So we're going to go KQ over R. That's 9 times 10 to the 9th, Newton meter squared over Coulomb squared. The charge is the big guy, 9 times 10 to the negative 9 coulombs, and then divide by 0.3 meters. That's the distance. So this gives us 270 volts. Now, remember I told you, do you care? Is it very helpful to know the electric potential at a single point? Not really. Okay? What the thing that's going to be important is knowing the change in electric potential between 2 points. So look at what's happening in this problem. In this problem, what we're going to do is we're going to bring this charge. So ready? I'm going to bring him in now. Let me grab this guy. We're going to take this charge right here, and we're going to bring him to infinity. Boom. We're putting him right there. Okay, and then what are we going to do to him? He's starting at infinity, and what are we going to do? We're going to take him and move him over here. Does this positive charge want to do that? Because at this point we know that positive charges want to move with the electric field, right? And you should also know that up the electric field, notice that up the electric field is higher volts than down the electric field. That's 0 volts, right? So this little guy does not want to go that way. So notice this building I have over here. Look, what would be the gravitational equivalent? The gravitational equivalent would be, so imagine you have an object here at the bottom of the building. If you grabbed this object and moved this object up to the top of the building, did you do work? You did. Work is done to move this object up the side of the building. Just like over here, work must be done to move the positive charge against the electric field, right? So what's the insight you need to have here? The work done in moving this object up the building is equal to what? It's equal to the potential energy gained. And I don't want to go back. This was from chapter 5. You know, to prove this, what you could do is write out that big long equation: kinetic initial plus potential initial plus any work non-conservative equals kinetic final plus potential final. This goes back to chapter 5. But long story short, the work done is equal to the change of potential energy, right? The same thing is true over here. So now, the equation we're going to use to solve the problem, here's what we do. So the basic definition, so by the way, what is our delta V between those 2 points? The change in volts is 270, right? 0 and 270, the change is 270. So what's the basic definition of potential difference? It's change of potential energy per charge. So the change of potential energy is going to be equal to the potential difference times the charge. The potential difference is 270 volts, but what's a volt? A joule per coulomb. And then what charge is being moved? That's this little guy. That's this guy. 3 times 10 to the negative 9 coulombs, and then the coulombs cancel. So this gives us the answer, which is 8.1 times 10 to the negative 7 joules. Final answer. The change of potential energy is the work done. Any questions?